Thank you very much for the introduction, Dean Freeman, and I'm thrilled to be here. My group is interested in extreme environments as found in the cosmos, including the conditions found deep within planets, where pressures can exceed many megabars or millions of atmospheres pressure. Inside these natural cauldrons of extreme pressure and heat, exotic materials may form. Remarkably, we can now reproduce these extraordinary conditions in the laboratory using devices such as these, so-called diamond anvil cells. With these devices, we can recreate the conditions deep within planets and probe the unique materials that form there using, for example, intense X-rays from the nearby Advanced Photon Source at Argonne National Laboratory, supplemented by theory done with high-performance computing. What these experiments and calculations reveal is astonishing, as shown here for this simple element, lithium, a metal with a simple structure and bonding at ambient conditions, but becomes enormously complex with scrambling of the electrons and bonds when compressed. Such behavior occurs across the periodic table of the elements with broad implications that span fundamental physics and chemistry, earth and planetary science, biology and biophysics, and the creation of new technological materials. I want to give you just one example, and that is the quest for room temperature superconductors. Superconductivity, or electrical transport without resistance, was discovered in mercury at the ultra-low temperatures of 4 Kelvin in 1911, which led to the Nobel Prize 2 years later. But if we could find superconductors that could operate at ambient conditions, that is room pressure and temperature, the results would revolutionize many technologies as listed here. In 2019, we predicted and then discovered superconductivity at much, much higher pressure temperatures of 260 Kelvin or 8 degrees Fahrenheit, which is near room temperature, and this exotic compound of hydrogen and lithium that exists, or lanthanum that exists only at very high pressures. This discovery helped galvanize a global search for related phenomena and other materials, leading to a report of superconductivity in an uncertain mixture of the elements lutetium, hydrogen, and nitrogen. During the past year, 2 very talented UIC graduate students, Alex Mark and Adam Ditchfield, successfully characterized the structure and superconductivity at this even higher temperatures and near ambient pressure. Their work was highlighted last June on the front page of the New York Times, and the first paper is being published in a journal this week. Moreover, their work has led to the prediction of new classes of ambient superconductors that could potentially be useful and commercialized. So this century-old dream of room temperature superconductivity, we think, is real. Thank you very much.